Welcome to Chapter 3. This lecture is going to be on minerals, the building blocks of rocks. So after this lecture, you should be able to tell your neighbor about the properties of minerals. I will give you a definition of what a mineral is. We're then going to move to the basic building blocks of matter, which means we'll talk about the subatomic particles of atoms. We'll talk about elements. We'll talk about minerals, and we'll talk about how those minerals make up rocks. So we first gave you an overview of what we expect you to know as far as the big picture in geology, and now we're going to go down to the finest bits. These are the subatomic parts of matter, and then we're going to build it back up. We're going to also talk about the different types of chemical bonds. In geology or in earth sciences, we usually consider ionic and covalent because they are the ones that do most of the action. We're going to talk about physical properties used for identifying minerals. We're going to talk about how geologists identify different mineral groups. We're then going to talk about how geologists classify rocks based upon their mineral constituents. Then we'll also talk about the natural resources extracted from mineral resources, and then we will end it at that point. So here we have quartz on the right, and it is a mineral. And so if you were to look at the definition of a mineral, it is a naturally occurring inorganic crystalline solid with characteristic physical properties and specific chemical composition. If I were to ask you if ice were a mineral, it would follow our definition. It's a naturally occurring inorganic crystalline solid with characteristic physical properties and a specific chemical composition, H2O. Water, which in the liquid, meaning liquid water, is not a mineral because it is not a crystalline solid, but ice, in fact, would match our definition, and therefore it would be considered a mineral. So, minerals are made up of matter, but what is matter? What is it? Well, matter is composed of subatomic particles, and in the nucleus of the atom, you have protons and neutrons, and then outside the nucleus, you have electrons. So matter has mass and it occupies space, which means it can't overlap with other matter, and it can't just pop in and out of existence. It has to be somewhere in space. It consists of atoms, and there are states of matter, which I think you guys are familiar with. There are liquids and solids and gases, and then there are plasmas, which we don't talk about much. They're found usually in stars. But all matter is composed of one or more chemical elements, and these chemical elements themselves are composed of atoms. So, except for some hydrogen atoms, which are a proton and an electron, the nuclei of most atoms have a neutron as well, and this basically is to balance out the positive charge in the protons so that they just don't fly away from each other, because like charges do not like to be close together. So electrons tend to be on opposite sides, as they show here. If you look at, excuse me, let me get a pen. If you look at hydrogen, which is one of the most simple, I put that in quotes in a sense, the most simple atoms, it has one proton and one electron, and they show it right here, one proton and one electron. If you look at a helium, now we call helium a noble gas. The reason we call helium a noble gas is because it has two protons and two electrons and two neutrons, which they don't show in here, and that is in the first shell of all atoms. There are two electrons, and in the nucleus there are corresponding two protons for those two electrons. Now if you were to add another electron, you'd obviously have to add another proton, but in helium, right here, you have two protons, two neutrons, and then in the nucleus, and then outside the nucleus you have two electrons, and that is the most stable configuration for the two electrons and two protons. It's called a noble gas because it doesn't interact with other elements and other atoms. Now we have a few others here, which if you look over here, we have oxygen. Oxygen has two electrons in that inner first shell. It has two electrons and four electrons, so you have this second shell, which is the P shell, which has 6 electrons. in this case, or if you were to consider the actual configuration, you actually have a second S shell, which they call the S1 and S2. In the S2 shell, you actually have 2 electrons, and then you actually have 4 electrons in the P shell. And because you have 4 electrons in the P shell, and the noble gas state for the P shell is 6 electrons, you can add 2 electrons, or you can share 2 electrons of your oxygen. Now, if you're neon, which is right there, you have 2 electrons in your S1 shell. You also have 2 electrons in your S2 shell and 6 electrons in your P shell. So in this case, this one right here is a noble gas. And so neon is just in the most stable state with 10 electrons, 10 protons, and 10 neutrons, and it does not interact with any other atoms. Therefore, we call it a noble gas. And we'll talk about silicon and iron and a few of these as far as oxygen too. We're going to put some things together, but I want you to take note that there are certain atoms that have all of the constituents, all the available spaces for electrons filled, and all the available spaces for the protons filled, and then those neutrons equal the number of protons, and you end up with this noble gas. And the reason it's a gas is because it doesn't interact with any other elements, which is how we get solids. And we're going to talk about that once we get to how atoms bond. So we have certain numbers that you'll see in the periodic table, or in this case they're just written underneath the nucleus, and then outside you can count up the number of electrons. We have an atomic number. The atomic number is the number of protons that you have in the nucleus. It's just a count. It's going to tell you what kind of element you have. You also have in non-radioactive or non-isotopic, which means this would be an isotope if you have one more neutron than you do electrons. But for carbon-12, which is most of the carbon that we have in our bodies, there are 6 protons, there are 6 neutrons, and there are 6 electrons. And this is a stable atom, but it still can share certain spaces in its electron shell with other atoms. Now, if you move on, we have these, we talk about radiocarbon dating. You've heard that. That's using radioactive isotopes in our bodies or in living things to figure out how long ago they died, because these have a certain half-life that can act like an atomic clock. Once you have a living organism no longer taking in carbon because it died, it could be a plant or an animal, it then starts radiating the carbon that's in its body, and over a certain amount of time, eventually this will all radiate away because it's radioactive. But if we get it at the right amount of time, we know that the half-life of carbon, so the half-life of carbon-14 when it decays is about 5,700 years. So if we have 2 half-lives, you know that this thing is a little over 14,000 years old, or actually 15,000 years old. No, sorry, let me rephrase that. I said 5,700. I meant 11,000 years old. I apologize. But if you look, they're different configurations. So this would be carbon-13. It's still carbon because it has 6 protons, as you can see right there. If you count up the number of electrons, it's going to have 6 electrons, but it's going to have 1 extra neutron, which makes it slightly unstable. One of these neutrons will probably decay, leave the nucleus, and you end up getting kicked back down to carbon-12, depending on what kind of decay process this undergoes. So the number of protons in an atom's nucleus determines its atomic number. And the atomic mass, which I haven't really talked about yet, is when you take the protons and the neutrons and add them together. So when we talk about carbon-12, carbon-12 has 6 protons and 6 neutrons in it. If you add them up, which is basically their atomic weight or atomic mass, is 1 for each one of those, because protons and neutrons are basically the same mass. You count them up and you get carbon-12. Now if you add 1, you have carbon-13. So you still have carbon. It has all of the same properties that carbon-12 does, because it's still an atom and it's still the element carbon, but it is radioactive. And then we have carbon-14, which then has 2 neutrons. It still has 6 protons, and if you count these, they also have 6 electrons, and they have the same properties as carbon, except for they're radioactive. So it's pretty simple once you understand. We don't really count the electrons because they weigh like 1,000 times less than the protons or the neutrons, so they just don't weigh a lot. So we don't really consider them when we're looking at the atomic mass. So if you have these atoms that have available spaces, or they are highly electronegative or electropositive, which means they attract other atoms, you can form a bond. And so ionic bonds, which is the first bond we're going to talk about, transfers one electron from one atom to the other. And because they are basically two poles of a magnet, once you do that, because they're one is positive, one negative, they're attracted to each other and they form a bond. So in this slide, if you look, you can see they are formed in a very regular structure. If you get into your kit and you pull out the halite, you'll see that the halite, it should be either broken up into little boxes. Don't break it up too much. You can even look at table salt if you want. It'll look like this as well, where you have all of these little boxes if you sprinkle it out. And that's because it has a cleavage. Salt cleaves in these little boxes that you see right here. It'll cleave out in a little box. Now these are really small. They don't really cleave like this. This tends to be a little bit bigger. But the reason they cleave that way is because they're sharing an electron, or they're not sharing an electron. They actually have exchanged an electron, where the sodium has given up an electron, and that electron is then transferred over to the chlorine atom, and the chlorine is then becomes electronegative, and the sodium, because it's lost an electron, becomes positive. So if you look at it, basically it's a bond where the atoms are joined by sort of electromagnetic forces similar to a magnet. Now if you look, this is a blow up of the middle figure that you were just looking at. You'll see that when we look at the sodium ion, it has in its stable or non-ionic state, it has 11 protons and 11 electrons. Now, the chlorine, notice it has 17 protons and 17 electrons, and it's much larger, at least the nucleus is much larger than the sodium, so the sodium could give up, excuse me. So the sodium ion gets a net positive charge because once it gives up one electron, it becomes more positive than it is negative, and it's attracted to the chlorine, which becomes more negative because it's taking an electron. Now, if I'm going to click out to the web here, and you guys should be able to see if you look at sodium and chloride. So here's sodium. Now sodium, in order to enter the noble gas configuration for its electrons, can give up one electron. If you notice, here's neon over here, where my pointer is, and it will be in the neon noble gas state. Now chlorine can gain one electron and enter the argon noble gas state. And if you'll note that it only has to gain one electron. And that's kind of what we have going on when you look at this figure. Basically, they're entering the noble gas state, or a more stable configuration, when they give up an electron or gain an electron. And when they do this, we call this an ionic bond, because they're now ions, which means that they have one more or one fewer electron, which makes them positive or negative. Now there's another form of bonding which we call covalent bonding. Now covalent bonding, basically the atoms share electrons, and when they share electrons, these bonds are very, very stable. And again, whenever you look at a periodic table, in this case, if you just count up the number of electrons, you can figure out what kind of atom it is. So if you look, it's 1, 2, and they're sharing one pair here, so that's one electron from this atom. So it'd be 1, 2, 3, 4, 5, 6. So if you look at it at 6, it's got to be carbon, because carbon is the one that we were looking at that has this kind of configuration. If you look at the periodic table again, we have right here, here's carbon. Now how many electrons can it share to reach the noble gas state? It's not going to strip away a bunch, because that would be much more problematic much more energetic. So it's just going to share electrons with some other atom. So in this case, you have 6. So there's the 6 I just talked about. I counted up 6. You can share 1, 2, 3, 4 electrons with other atoms, which puts you in the neon noble gas state, which means you're in a very stable configuration. So let's go back and look at our figure here. If you look at the figure, we have, here is 1 and 2, and now I said it can share 4. Well, here's 1 right there, right? That would be 2. Here is 3, and there is 4. And the other pair here, this is from this atom that's over here. This one right here is from this atom over here. This one is from this atom right here. And then this one is from this atom right here. So if you notice they're sharing 4 electrons with other atoms, and so they are in a very stable configuration. And these are also other carbon atoms that surround the one that we were just looking at. Now, there are different ways to show these covalent bonds. This is a standard model where you show the different electrons. I'm going to show you something. We'll use water, so it's something that most people recognize, and I'll show you how to do some of these things. Excuse me, sorry. When you look at this model right here, which is just the ball and stick model, if you look, each one of these sticks that you see that connect the little balls, they are one bond, but they actually represent 2 electrons that are shared. And when you look at it, you can count up the number of shared electrons, and you have 1, 2, 3, 4. So these are also carbon. This is actually the configuration in quartz, and this is the configuration you would see in mica, which is also specimens you have in your kit. So let's look at, I'm going to just make an extra slide here, so give me a second. So in our extra slide, I'm going to show you something that's, I think, pretty cool and pretty easy to understand. I'm going to just make an H right here, and I'm going to tilt it for a reason. I'm going to make another H right down. These are hydrogens. Now, if you look at hydrogen by itself, we'll often draw an H and we'll put a circle next to it, which means it's hydrogen and it has 1 free electron, which means it can share 1 electron. If you look at the periodic table, you'll see it's the very first element, and that very first element can then share 1 electron to enter the neon noble gas state. I'm going to draw another red right here, and I'm going to draw an H so that you can see that this red H, even though these are both hydrogens, they're sharing 1 electron with each other, and they're in the noble gas state. Now this is a very reactive state. This is, when hydrogen is bound to itself, it's called H2. Now this, you can see why it's H2. There's 1 there, and there's 1 there, there's 1, and there's 2. Now when we look at that, it's very reactive because you can oxidize this. If you were to expose this to oxygen, so light it on fire in a sense, you'll see fire, which is the energetic exchange, the release of energy as these electrons reorient themselves. You actually would end up with something that I'm going to draw right over here. I'm going to make the oxygen red, just like I did the hydrogens over there, and it's O, and I'm going to put 1 dot there and 1 dot there, signifying they're sharing these 2 electrons. And I'm going to put 1 dot here and 1 dot here to show you where the hydrogens are sharing. And then I'm going to put the other electrons around the oxygen so it looks like that. And so what you have is, if you look at the periodic table, oxygen is, well, let's just do that. Here's the periodic table. Here's oxygen, and how many spaces can it share with other electrons to fill up that outer electron shell? You have 1 and 2 to enter the neon noble gas state. If you look at hydrogen over here, how many can it share with other atoms is 1 to enter the helium noble gas state. So we're going to share 1, 2 with oxygen, and we're going to share 1 electron with the hydrogen. And that's in fact what we have if you look at water. This is H2O. There's the H2, right? 1 and 2, and there's 1 oxygen, as you can see right there. And we can write this a variety of ways. I could write the oxygen like this, which you all often see. And like I said, if you see, this is just the symbol for the atom, or the element, excuse me, the symbol for the element, and then we just draw a stick to the next symbol of the other element, which gives you, we know that they are sharing 2 electrons, but this signifies 1 covalent bond. When you put all these together and you look at how they bond, if you look at how we were just looking at water, it bonds at a specific angle. That's why it looks like it's sort of like a V with the H's on the top and the oxygen on the bottom. They form specific crystals because of the shapes of all the different atoms that make them up, or not the shapes, but the sizes, and then the bond angles of all those different atoms when they connect as they're sharing those specific electrons. They form specific types of crystals. You've already seen the first crystal here. This first crystal is salt, right? It's a cuboid type of configuration. This octahedral kind of configuration right here would be the kind of garnets you would find on sandpaper. They are kind of red. This is fluorine. It's sort of the Zelda crystal, if you guys played Zelda, and of course we have the standard quartz crystal right here. And they all have these configurations because they have specific bond angles associated with the atoms that make them up, that make up the molecules. So if this is silicon tetroxide, it only can form, I mean, these are all basically silicates except for the salt, of course. These are silicate type of configurations. And we know based upon the crystallinity, sorry, there's a thing it just says it's wrong. I don't know why, but it's a correct spelling. But the crystallinity of minerals, the different specimens of the same mineral show consistency of these interfacial angles. Interfacial means inside the crystal. If you were to go behind the crystal and then measure the angles, you actually have a goniometer to measure crystals, and you can be a little bit creative in how you use the goniometer to measure the crystal faces, but you should be able to do it. And we have very specific crystalline structures based upon these bond angles, or in this case, the angles of all of the different layers and configurations once they built up will be 120 degrees if you were to look at any one of the quartz crystals. Now, amorphous materials like glass, which these are silicates, but they don't have crystalline structures, won't have any bond angles associated with them, and so they don't look like crystals. So an interesting problem is so here we have smoky quartz. I think this is from your book. I think that's smoky quartz on the left, and we have rose quartz on the right. And so the question is, why is it that, okay, they're crystals and they are minerals. Why don't they show well-developed crystal structure? And, minerals form and grow. They don't necessarily merge together in this very obvious interlocking crystalline 120-degree sort of interfacial structure. They can bond in ways that don't appear to be crystalline at all. In this case, I think it's because they broke these out. I mean, these are rose quartzes, but if you break them out, they break like glass. They have conchoidal fracture. But the individual minerals that make up all of these different mosaics of the different atoms are three-dimensional framework, and if you were to look close enough, these would have a 120-degree bond angle between all the silicon tetroxide if you were to look at this, really, really close up, as in the using microscopic sizes. And then we have some minerals that, this is silver, I think, that don't really look like much of anything, but they do have a specific structure. It's just really small. So think of it like the pixels on your computer. Your pixels on your computer, they're so small that if you The picture that you're looking at is actually made out of little squares. In a sense, that's sort of a crystalline structure, but they have different, different colors, etc., associated with them. But they can only be square. But if you put them close enough together and they're small enough, it looks like it's a curved sort of angle. Like if you look right here, this looks curved, but in reality, that's all a bunch of little square pixels that are making it up. So by definition, when you look at all of the native elements, in this case, we have gold and we have diamond and we have some silver and copper. They are composed of a very specific kind of structure, and there's crystalline structure here, but it's very hard to see because of how small they are. If that makes any sense. And also, some crystals can vary because there are some elements that are of the same size that are substituted. And the next slide, I think, is going to show that. And that basically, so if you look at olivine, which I think I use it as an example somewhere in the notes, it's composed of silicate, like it's a silicon tetroxide, but it also has, which is sand basically, and it has magnesium and iron in it, and it can be composed almost entirely of magnesium. So 100% of the different ions that separate the different silicon tetroxides in the crystal can be magnesium, or they can be, well, actually olivine isn't have a crystalline structure, so I shouldn't say that, but in the actual mineral itself, the crystalline structure that we can't see because it's so small is like, could be all iron. It could be 100% magnesium separating those different silicon tetroxide, or it could be 100% iron. So just be aware of that. So the crystalline structure isn't sometimes obvious, like as you see in the silver right here, or it's not what we expect because the way it grows is kind of odd. But we can intersperse, or I should say intersperse, we can change some of the components of the minerals based upon the sizes of the different atoms that make them up. So I was just talking about iron and magnesium. If you look at iron and magnesium, they're very, very similar in size. So this is 0.72, this is 0.63, so they often will take place of each other in different minerals. We use different physical properties based upon the molecules that make them up when you look at crystals. So there's a hardness property, which you guys will be looking at. You have the crystal form, which is sometimes apparent, sometimes not. You have luster, so it can be metallic or non-metallic. We also can use certain physical properties that are controlled by the chemistry. So if you take some, we use vinegar, we use hydrochloric acid in the lab, but if you were doing this at home and you want to find out if something is a carbonate rock, you can take vinegar. It just reacts much slower, but it will effervesce or bubble. It just takes some time for those bubbles to form if you're using vinegar rather than hydrochloric acid. But that is a special property of rocks that have carbonates in them, or I mean minerals that are carbonate, like calcite. And when you look in your book, most of the minerals that we're looking at are composed of silicates. Usually there's some carbonates and some sulfates and some other things, but primarily they're silicates because there's just so much silicon in the Earth's crust. So the number of minerals is limited by the number of elements. There are quite a number of elements. We have 92 naturally occurring elements. 8 of them are very common. The 8 are listed in the book and in this slide as well. The most common minerals are made up of oxygen, silicon, and a few other trace elements, or elements that aren't as common, so there's just less of it. We have iron and we have magnesium, like I said before. We also have some calcium and sodium and potassium. So if you're looking at certain feldspars, they'll be interspersed with potassium, sodium, and calcium. And then you have the darker feldspars, which are going to have maybe the darker elements in them, magnesium, iron, a few other things. And I show you this slide not because I want you to memorize the different types of mineral groups, although they are good to know if you were to take an exam, but out of the 3,500 known minerals that are silicates, which are compounds of silicon and oxygen, we basically just group them together and call them silicates. So if you look right here, we have a silicate, which is quartz, silicon dioxide here, but then they come together to become silicon tetroxide, depending on how they are the configure of the charged ion or the what they call the radical that composes them. But it's they're 3,500 silicate minerals, so we just call them silicates, if that makes sense. Otherwise, you're going to spend a lot of time naming them. And this is what they look like. So we have a specific mineral group, and it's going to have specific characteristics based upon the configuration of these silicon tetroxides that are inside each of them. So here we have, if you look at the first one here, we have olivine, right? Olivine is composed of silicon tetroxide, and it's isolated tetrahedra, and it does not share the oxygen. So if you look right here, these oxygens are available to be shared, right? They have different configurations here, but it doesn't share any oxygen, which is why when you look at olivine, it doesn't really have a crystalline structure like you would look at the pyroxenes of the amphiboles here. Hornblends, the micas, the muscovites, these are the big sheets that I was talking about. These have specific crystalline structure. Now, it's not that these aren't crystals. The olivine has these individual units, which they just are connected in a very, not amorphous, but a way that is not repeatable like you have in the pyroxenes or amphiboles or in quartz, which is a much more complex system where all 4 oxygen atoms are shared, which is a very solid 3-dimensional mineral. And I'm going to quickly go through the different silicates and different groups. We're not just going to do silicates, we'll do carbonates and some other things. So you have the ferromagnesium silicates, which contain iron and magnesium. That's what ferromagnesium means. And they are dense and usually very dark. So you have the olivines, the amphiboles, the pyroxenes, and the biotite, as you see there. Then we have the non-ferromagnesium silicates. These are the minerals that lack the iron and magnesium. That's why they're non-ferromagnesium, and they contain primarily aluminum, calcium, potassium, like I said before, although I skipped aluminum, but they also have a few other trace elements in them, but they are light colored. That's because calcium, potassium, and aluminum are light in color, and so you end up with the quartzes, the potassium feldspars, the plagioclase feldspars, and the muscovites, which is another type of mica. The mica that is lighter colored, and it's also from the Muscovite region. They used to mine it up in Russia. That's why it's the Muscovites. If you know anything about history, it's because that's where they used to mine muscovite, and they used to use it as windows before we knew what to do with glass or melting silicate to make glass. And then we have the carbonate minerals. Now the carbonate minerals are carbonates. That's CO3, which means it has 1 carbon, 3 oxygens. It's bound as a unit, and it's -2 charge. And so calcite is calcium carbonate, and dolomite is calcium magnesium carbonate. They are mostly found, these minerals are mostly found in sedimentary rocks, limestone and dolostone, but here we have just the carbonate mineral. And carbonates primarily are derived from shells and hard parts of marine microorganisms that precipitated from seawater as evaporites, which is, big layers of carbonate, calcium carbonate, from the shells of these organisms. Then you have the native elements, which I was talking about before, and here we have diamond on the left. You have, looks like gold on the bottom and copper on the right. We have a lot of these displayed, well, not the gold and the diamonds, because people would bust in and take it, but we have a lot of copper, which is not really precious, but we have some really cool copper nuggets in McDivitt if you guys want to come and check out the specimen cases. Then we have the sulfides. These are, you have some of these, you have the galena, which is the lead sulfide, and you have the pyrite, which is the iron sulfide. These sulfide minerals are found in pretty much all types of rocks, and they are commonly found along the mid-oceanic ridges because of the iron and lead and magnesium and stuff, and the sulfur that's available because of the volcanic activity. Here, this is fool's gold. Now, you look at your specimens, you'll know why people thought it weighs a lot, it has heft, and it's gold, and so people used to think, oh, I struck it rich, when in reality it's really not worth all that much. And then you have the sulfates. These are barite and cerussite, and then gypsum, and these are sulfates that form some very interesting structures. We have barite roses. You can come check those out in the lab. They look like a rose, and it's made out of barite. And then you have gypsum, which is calcium sulfate with some water in between. The gypsum would be sheetrock, the kind of stuff you put in your walls. They use gypsum to make sheetrock. And for some reason, my dogs like to eat it. I don't know why. I don't know why they think it tastes good, but they always eat holes in my walls. It's kind of funny. But these are all formed from the evaporation of water. These are called evaporites. Then we have the different physical properties that you guys are going to use to identify these. And the reason I show you the picture here, and I think this is the picture from the book, is it's an agate and it's quartz, and it's very, very hard to identify minerals based upon color. And the reason is because they take on many different colors. So if you look right here, this has a whole bunch of different layers. So here you have a brown layer. Right here there's a red layer and more brown layers and a deeper red, and then you get into some blues. This is due to like iron and copper and a few other sort of these minor elements or minor parts of the whole structure, but they add a lot of color when they do that. So primarily we look at luster, which is going to be metallic or non-metallic, I think, as far as we use the dichotomous key. You look at hardness, you look at if it has cleavage or not, if it's a conchoidal fracture. You look at the crystal form, if there are any crystal forms. Some of them don't show their crystal form very well. And then the specific gravity, which is a density. You're going to learn how to do density. Laura's going to have you go through a density lab, which is a really cool way of identifying or figuring out not just what kind of minerals you have, but also what kind of rocks you have. And you're probably going to use Mohs hardness because you have everything but the diamond. You have in your kit, you have the corundum, the topaz, quartz, orthoclase, apatite, fluorite, calcite, gypsum, and talc. And we use, there's a glass plate we use, steel file, but you can actually use just using Mohs hardness scale and your mineral kit. You can figure out the hardness using these minerals right here, the hardness of the different ones that you're looking at. So basically it's a relative hardness scale, but it works pretty well. So you know that you have a apatite, which is your teeth basically. That's a calcium phosphate in a sense. It's a crystal, but yeah, I don't know if you guys knew that your teeth the enamel in your teeth is actually a mineral. It's an apatite. But the glass is 5.5 to 6, or you can use the apatite as, you can scratch apatite or use apatite to scratch other softer minerals. You can figure out the hardness of those minerals based upon the apatite. Now the specific gravity, the density, that's basically when you look at the mass to volume ratio. So specific gravity is a way to describe how heavy a mineral is. It's heft, really. It's not really how heavy it is, but how dense it is, how closely packed those different atoms are. And also the size, because obviously lead they're very big. If you look at the periodic table and you look at lead is going to be down here. They call it plumbium. That's what it was originally because it was in Latin. But it's lead. It's 82 protons. Its relative atomic mass, or actually the atomic mass, is 207. And that's pretty heavy. I mean, that's really a big atom. And if you put them all into a big structure, they're going to weigh a lot. And they're going to have a lot of mass. So galena, which is in your sample kit, it has a density of 7.5, which means it's 7.5 grams per cubic centimeter. And the density of water, once you guys do your liquids in the lab, it's 1 gram per centimeter cubed rather than 7.5 grams per centimeter cubed. And now when you get galena and you look at the specific gravity, it's 7.58, and it's unitless, because when we use the specific gravity, or we compare it to the weight of water, the actual comparison makes it unitless, which again it's a way of figuring out the density, but it's not actually the true density. It's just a way we're comparing it to water. We also have special properties. So some useful properties are they feel talky, or it might feel greasy or something like that. And there's also taste. You can taste the halite. I wouldn't taste your minerals. It's not a good idea, just because there are a lot of minerals that are poisonous. You don't want to lick lead. Lead sulfide's not good for you. It can affect your brain. So be aware of it. And there's a little warning in your kit that says don't handle the lead. I wouldn't worry about it too much. I used to, put lead shot on my line whenever I used a sinker when I was growing up, and I seem to turn out okay. At least I think I have. We also have magnetism. You have magnetite in your kit. You can use magnetism. And then there's double refraction, which is the calcite. So you look through it. If it's clear enough, you'll be able to see two images. And then there's the dilute hydrochloric acid, or in your case, you should use vinegar because you don't want to be handling hydrochloric acid at home. But the calcite and the dolomite. Dolomite's much harder. You got to crush it actually in order to get this effervescent or this bubbling to occur. Calcite's a lot easier because it's basically calcium carbonate. Dolomite is the magnesium calcium carbonate. Now when we look at the different minerals, I show you this. This is from the older book. So if you guys have an older book, you'll be able to look at table 3.3, but it's in there. I mean, I don't know what number it is in the new one. I should probably look at it. But you have olivine. Those are very common. The pyroxenes, the amphibols, and the biotite. And when we start identifying rocks, you're going to have to look at the relative percentages of these different rock-forming minerals in your rocks. You have quartzes, the potassium feldspars, the plagioclase feldspars, the muscovite, that's the light-colored mica, and the clay mineral groups, and then of course the carbonates. These are all different mineral-forming non-silicate type of minerals. But there are many, many minerals, but we use these to say that they're basically the most common. So we'll say, why do we call them rock-forming minerals rather than other accessory minerals, which are, like kryptonite? Kryptonite actually is a real thing, and they discovered it up in Russia somewhere. I know. You can find the article somewhere in the news, but a few minerals are just so common that we call them rock-forming minerals. That's why we do that, so that we can identify the different types of rocks. And you'll look at the granite that you have, and it has a whole bunch of plagioclase feldspar, some quartz, some potassium feldspars, and some biotites. And you can just take a ruler and run it across, put it overlay over the top of your granites or whatever, and you can count up the number of minerals, and you should have a certain percentage of light-colored minerals versus dark-colored minerals, and it'll come out to be like 0 to 15% dark-colored minerals, which means it's a light-colored rock. And so basically what happens is they precipitate as they cool, and since most of the, magnesium and iron sort of rocks have precipitated first, the last things to precipitate are these lighter colored, more stable sort of rocks, and these are the granites. But they tend to have the same distribution from 0 to 15% of the ferromagnesium minerals, which means there's less dark-colored minerals. It's usually biotite and some feldspars that make it a little bit. I did say I was going to talk about the natural resources and reserves. Now, if you look, we actually are number 10 now. I think in the new book we actually have moved into number 10 because I don't know what we're doing. I think we're starting to mine the iron again. But actually I think it's quarry rock, not mining iron. I know we're starting to mine iron again, but there are some interesting caveats associated with how the United States is dependent on imports or other mineral resources. Canada tends to be more self-reliant in the kind of stuff that they're doing because they don't use as much as we do. And you also think about all of our little iPads and iPods and your little phones. We don't make iPods anymore, I guess. But all of the phones you guys use, they are made from quite a lot of important minerals, these rare earth minerals that we don't really have in the United States. So this is something to be aware of if we want to continue using the stuff we want to use and not be at the beck and call for other countries because they have the resources that we don't. So in summary, we have matter has mass and takes up space. The elements are composed of protons, neutrons, and electrons. The minerals are composed of elements and have specific physical properties used to identify them. We have specific minerals that are more common than others, and geologists put them into mineral groups, and we use those to identify the rocks. Most natural resources have a mineral source. I didn't really go through them because it's not really, we can find, gold in the Rocky Mountains because that's where you find the quartz veins and other things associated with those gold deposits. And it's also because we had the uplift from the mountains exposed old ocean, shallow sea vents from divergent plate boundaries, etc., that precipitated all of those minerals. And so be aware that it's areas where we have these old shallow seabeds that were uplifted that we find a lot of these rare earth minerals that we like to make phones and computer chips and other things from. So it's something that we have to be aware of when we're thinking of how to move forward and how our industry is going to be affected by the kind of natural resources we have. So that concludes this lecture. I guess I will return when I do lecture 4.